Thanks everyone for coming. This is the first Quantum Papers Behind the Curtains talk, and our speaker will be Andi Li, and he's going to talk to us a little bit about his research, and then we're going to go into a discussion.
So good morning, everyone. So thanks for coming. So I'm a PhD student in physics in Dr. Hrvoje Petek's lab. And today I'm going to discuss my recent papers on the topic of multiphoton photoemission spectroscopy of silver surfaces. So first, to translate this title, we are studying how the single crystal surface responses on the light-matter interactions. So when we shine a light onto the surface, we will have electrons excited, and we can use this to study the electronic structures and the excitation pathways in this surface. A powerful technique, after a brief introduction part, I will divide my research into two parts. First, so to study why we are studying the electronic structures, because it serves as a fundamental research topic in solid-state physics. So it determines the various material properties like optical, electronic, magnetic properties. A powerful technique to study the electronic structures is the ARPS, the angle-resolved photoemission spectroscopy. So for example, if we take the graphene and iridium boron as an example, we can use a high-energy photon to excite the occupied part of the band structure, and we can map out the dispersion of the two branches of the surface state. However, if we want to study the unoccupied part of the electronic structure, we need to reduce the photon energy range to induce two-photon photoemission. For example, the purple arrow here first populates the unoccupied part, and then the red photon emits this part. In this case, we can map out the dispersion of the unoccupied states. So in our lab, we specialize in multiphoton photoemission, where we use two or more photons to excite the surface. So next, I will briefly describe the band structure of what I studied, the noble metals. I will take the silver 101 as an example. So this is the Boolean zone of the box silver. So when we have a surface, we will project our band structure in the Boolean zone along the 101 direction to get a surface projected bulk bands, which is the lower and upper ST band, which is the shaded area. They are separated by a band gap. Because we are studying surfaces, there will be surface-induced states. The first kind is the Shockley surface state. It arises as the boundary condition of a semi-infinite crystal. So the atomic layer terminates at the interface, so there will be an induced surface potential. Solving this potential will give us the Shockley surface state. And for silver 101, it locates slightly below the Fermi level. Another kind is the image potential state. So this is because when we excite a photo, we have photo-excite electron. When the electron is in front of the metal from the electromagnetism, there will be an image potential. So solving this additional potential in the Schrödinger equation will give us a series of states, which we call the image potential states. So for silver 101, the first image potential state lies in the band gap, and the higher order image potential states will convert to the vacuum level. And I will also describe my result on silver 110. So silver 110, it is we are projecting our surface in this direction. So from gamma point to the red point over here. We will see later that these different orientations will give very different material properties. To study the photoemission, first we need the laser. So our tunable wavelength laser give us the tunability from the infrared range to the visible range. And by further frequency doubling it, we can achieve the UV range. And after the laser is shined onto the sample, we can collect our photoelectron and analyze the energy and the parallel momentum of the photoelectrons. And we can get a photoelectron spectrum. So this is the energy axis, and this is the parallel momentum axis. We can see different peaks, which comes from either surface states or the bulk states. Okay, next let's jump into the first part. So we are studying silver. Silver is a model system in surface science, and this is a atomic structure of the silver 110 surface. We can see that in the orthogonal direction, the atomic structure is largely different. This will result in a very prominent feature of this surface, which is usually measured by the reflectance anisotropy. So basically, they are measuring the optical properties along the orthogonal directions, and they can find a large difference when they take the difference of the two direction results. Silver 110 has also been widely used for substrates. For example, the silicon nanowire can grow in a specific direction along the silver 110 direction, silver 110 surface. It can also, if we deposit atoms or molecules on the surface, we can also use the orbital imaging technique to image the wave function of the atomic or the orbital or molecular orbital. And they can also grow the molecular nanostructures on it. It can also be used for be used in experiments of photocatalysis experiments. However, this surface has seldom been studied by spectroscopy. So one reason is because its special structure. So we can compare this is the silver 111's spectrum, and we can see our measurable K parallel range is only plus minus 0.2 inverse Armstrong. Corresponding in the band structure, it is only a very limited range. And for silver 110, this range is kind of boring. The interesting of the silver 110, the band gap and the surface states, they lie deep in the Bourian zone. However, to excite the electrons deep in the Bourian zone, we need to overcome a barrier which is called the photoemission horizon. This is generally because when the electrons are deep in the Bourian zone, they will have it will possess a part of the energy which is in the surface parallel plane. However, when the electrons are photo-emitted, only the surface normal plane can do work against the work function. So at different K point, we will have a lower limit in energy of the electrons. So which is this green parabola, which is called the photoemission horizon. So if we use 3 photons to excite the electrons in the gamma point, we can detect it. However, if we use the same process in around Y point, we cannot detect the photoelectron because they didn't overcome the photoemission horizon. A common way to solve it is to use sufficient high energy photons. For example, use high harmonic generation photons so we can have enough energy. So in our group, we are increasing the field strength to induce higher order photoemission process so that we can excite electrons above the photoemission horizon. So by this, we solved one part of the problem. However, there's another point which is because of the anisotropy of the silver 110 surface. As I have already said that the silver 110, it is largely anisotropic in different K direction. However, our setup only have the one-dimensional resolution. So we can only measure the energy spectrum along one K direction at a time, which is very inconvenient. So at the beginning of 2020, I got a chance to visit University of Göttingen to use their setup, the time-of-flight momentum microscope. Basically, they can collect all the electrons from the surface and analyze it and generate a 3D data set, which have energy versus two-dimensional momentum resolution. So this is the sample data. So this is the energy axis, and at each energy slice, we can map out the full two-dimensional momentum range. To analyze this data, we need to cut it into two-dimensional 2D cross sections. For example, this is the two-dimensional momentum cut at the Fermi level, and these two are the energy spectrum along the gamma Y and gamma X direction. We can observe, very complicated structures. So we want to assign these structures. So based on this, we have a theoretical calculation on the DFT band structure of it. So we assign all of these states to the single particle band structures. A part of it is a purple colored states are the bulk transitions, which I won't spend time on it. And the other red labeled states are the surface states. For example, we can excite this S1 surface state. We can excite both the occupied part and the unoccupied part of the state. We can also excite the unoccupied S2 states. Also, at gamma point, we have this additional S3 state. I will elaborate on this state in the second part of the talk. To augment these assignments, we increased the nonlinear order to induce a 3pp and a 4pp spectrum. So these two are the corresponding spectrum. So if we can see that when we look at this yellow and the red dashed lines, these are the dispersions I extract from the 2pp data, so from the previous data, and plotted at the corresponding energy position. We can see that it matches with the experiment spectroscopy features, and also in the other data, the energy position and the dispersion also match. So this confirms our assignments of the states to these two surface states. And in addition, we have also observed the image potential state theories. So the image potential state the intensity largely depends on the K parallel, which you can see at a gamma point, we have very low signal. This is because the image potential state is degenerate with the bulk bands, so it will decay very fast. However, when the image state enters the band gap, it forms a discrete surface state, and so we will have very strong surface state signal. Also, it can be enhanced when it matches the resonance condition. For example, here there is a one photon resonance between the S2 state and the image potential state, and we can see over here that there is a crossing, nearly a X-shaped feature over here, and we can see at the crossing point the intensity is enhanced. So basically, we study the 2 photon emission, 3pp and 4pp, and present a comprehensive study of the MPP spectroscopy of the silver 110 surface. So next, I'm going to discuss about the plasmonic photoemission from silver surfaces. So silver is a widely studied plasmonic material. So plasmonic material is of broad interest, potentially because there have potential applications. For example, the plasmonic waveguide. They are believed to carry more information than the electronic wire we are using now, and they have little problem in dissipation. It can also be used in some chemical reactions or medicines. So because plasmons can couple light into the electron energy, so this energy can be used to, for example, kill the cancer cells or excite the electrons from the ground state to catalyze the chemical reactions. However, most of these applications involve the surface plasma. What about the more intrinsic bulk plasma response? Another question is the energy conversion efficiency. For example, when it is widely assumed in the plasmonic community that the plasma decay will generate hot electrons in a broad energy range from the Fermi level to a plasma energy above the Fermi level. I will show in our data that the bulk plasma decay preferentially excites the electrons from the Fermi level, which is a high conversion efficiency from the plasma to hot electron. To study the bulk plasma response, we need to first study the dielectric function of silver. So this is a real part of the dielectric function, and when it's end with 0, it defines a region called the epsilon near zero region. This region defines the bulk plasma frequency. And below this, if the photon energy is below this bulk plasma frequency, the silver has a very effective screening and low loss in its optical properties. So this will result in the perfect reflection of the light, which is why we are using silver mirrors. From the theoretical calculation, we can show that calculate the electric field strength outside and inside the surface. So we can see that the electric field strength is very small and evanescently decays into the bulk silver. However, if we increase the bulk plus photon energy excitation, photon energy above the bulk plasma frequency, we can see that there's a large considerable amount of electric field inside the surface of this is the surface, and inside the surface the electric field strength is large. So in this case, the external field penetrates into the silver. So to study the bulk plasma response, we scan all photon energy across this epsilon near zero region. So we first start with a low energy excitation spectrum. So this is, we have already seen it, and this is the bulk SP band transition. This is the Shockley state transition. And if we increase the photon energy, we will see the shifting in the energy position of these two states. This is because these energies gain energy from the photons. And if we keep increasing the photon energy, we can also see that the image potential state, the Shockley surface state, and in addition, we have this additional peak in this shaded area. We can also look at it in this two-dimensional spectrum, where the surface state feature, they are shifting with photon energy, and this additional peak is hardly tuned with photon energy. If we plot the peak energy position and the intensity of the peak with regard to the photon energy, we can see that this additional peak, it only appears after our photon energy is above the bulk plasma frequency. And also the energy of this peak hardly tunes with photon energy. In the silver band structure, we cannot find a final state which is in a fixed energy position at a different photon energy excitation. So this peak cannot come from photon excitation. So we attribute this to the bulk plasma frequency, bulk plasma excitation, because as long as the photon energy exceeds the bulk plasma frequency, the bulk plasma field's energy is more or less stable in energy. And from analyzing the energy position of this peak, we have seen that this peak is actually directly from the Fermi level. So we are exciting the bulk plasma. The bulk plasma decay excites the electrons preferentially from the Fermi level. And since this is a bulk plasma response, it shouldn't depend on the single crystal orientation. So we also studied the silver 110 surface, and also did the with photon energy dependent data. Because around the gamma point, the silver 110's band structure is kind of lacks bright spectroscopic features. So the only feature we can observe here is the Fermi level, the two photon emission from the Fermi level. However, if we increase the photon energy, we will observe a enhancement in this photon in the Fermi level signal, and above this bulk plasma energy excitation. Similarly, this peak hardly shifts with the photon energy. If we rotate the silver 110 because it's anisotropic, and we can get a similar result where the we observe a peak which hardly tunes with photon energy. So we claim that we also observe the bulk plasma excitation on the silver 110 surface. However, one special thing about the silver 110 surface is from the DFT calculations, we have a surface state. We observe a state with strong surface character around 7 eV, which is in the final state energy region. And if we compare the experiment data with the theoretical calculation, we can see that along the gamma y direction, the state is strongly dispersive, and our signal localized at the band minimum. And if we compare the data with the gamma y direction, gamma x direction, the theoretical calculation is, less dispersive, so that our spectroscopy feature is following the dispersion of the theory calculation. We also compare the two-dimensional momentum cut of this state. So the black dots over here is the two-dimensional density of state calculation, and we can see it reproduce our peak dispersion nicely. So we claim that for silver 110, our bulk plasma decay excites electrons into this S3 state. Another very interesting thing about the silver 110 is the polarization dependence data. So along the gamma y direction, this is a p-polarized light excitation, and this is the s-polarized light excitation. And we can see that the signal in p-polarized light is higher in s-polarized light. This is the same with silver 111 or 100, and matches our expectation, because for the metal surfaces, the s-polarized light is pure in-plane component. And because of the screening on the metal surfaces, the total electric field in the surface plane, so parallel to the plane, should add up to 0. So we should expect less photoemission signal in s-polarized light. However, if we take a look at the gamma x direction measurements, we will see that the secondary electron age, it will still have the highest electron counts in p-polarized light and the lowest in s. But for the bulk plasma peak, we have a very stronger signal in s-polarized light. In addition to this screening on metal surfaces, another important point is that under surface response theory, the bulk plasma excitation needs surface normal field. So in principle, s-polarized light cannot excite the bulk plasma. So we are explaining this by the special atomic structure of the silver 110. So in the gamma x direction, we have the silver atom rows, and along the gamma y direction is a corrugation. So we have the atom rows and the atomic troughs. And we can find out that no matter when the s-polarized light, when the sample is aligned in the gamma x direction, or the p-polarized light, when the sample is aligned in the gamma y direction, they both have an electric field component in the gamma y direction, so along the surface corrugation. And if we have also finding literature the theoretical calculations of the surface states in the band gaps. What their calculation shows that one of the states, the wave function localized between the atom rows, so in the troughs, and another surface state is located at above the silver atom rows. So these two states, they are laterally displaced. So in this case, a surface electric field which is along the surface corrugation can couple these two states and generates this charge density oscillation, and this polarization field component can have a surface normal component, which excites the bulk plasma. This has also been observed in some similar experiment. For example, the surface second harmonic generation signal. In their experiment, they also observed that the surface states the second harmonic generation signal from the resonance of the surface state, it will be enhanced as long as we have an electric field component along the surface corrugation. So as a conclusion of this part, we have studied the silver 111 and silver 110, and the silver 100, which I didn't show here. We at the epsilon near zero region, we have both observed the bulk plasma excitation. The epsilon near zero material has for the material in the epsilon near zero region, for example, the reflectivity of the metal surfaces, we can observe a abrupt change in the reflectivity in this epsilon near zero shaded region. So scientists expect that the optical properties will abrupt change in this region. So they propose the optical switches using epsilon near zero material. And the second point is that our bulk plasma decay preferentially excites electrons from the Fermi level. So this conversion from plasma, whether it's preferentially excites from the Fermi level or it excites hot electrons in a broad energy range, at least our data shows that this preferentially from the Fermi level is correct. But since the most applications are about the surface plasmons, and surface plasma still has some different with the bulk plasma. So whether this result can benefit the surface plasma, research still needs further consideration. And another point is for the silver 110 surface, we observe the unconventional bulk plasma excitation, where we need to consider the surface corrugation, so the atomic scale structure, when we are thinking about how the plasma are excited. So as a conclusion, in the first part, I described the multiphoton photo emission from the anisotropic silver 110 surface. So we first extended the MPP area of interest from gamma point to deep in the Bourian zone. And then we have presented a comprehensive study of the silver 110 spectroscopy. And so the technique and the research has been published in separate 2 papers. And this is a 3D photoelectron spectrum taken from the data where this are the two-dimensional momentum range, and this is energy range. So it's drawn in a 3D way. And in the second part, I discussed the plasmonic photoemission from silver surfaces. I don't want to repeat this the 3 points I have already said. And this part has been published in 2 papers, and the corresponding theoretical work has also been published in a separate paper. And this figure is a summary of this plasmonic photoemission on the silver surfaces. And for the acknowledgement, this is a collaboration between our Pittsburgh team, the University of Göttingen, and our theory calculation from Institute of Physics, Ziegler. And thanks for your attention.
Thanks, Andy. Great talk. I'll ask a question to get things started off. This one's going to be just technical. I'm more from a theory background. We'll do introductions whenever we start the discussion. But how well does DFT actually describe some of these things? Some of them sound like they're like, at least the plasmonic stuff and also image potential states seem like DFT might struggle at capturing.
Sure. Because DFT mostly is calculating the single particle band structure. Yeah. So actually, for example, this state is actually a single particle band.
Yeah.
But it's only that this is plasmonically excited. So from the calculation, we have this band, but we don't know whether it can be excited or excited by a specific region in the lower occupied part of the band structure. But from the experiment, we cannot find a specific region of the bulk ST band which is active under the light interrogation. Yeah, so basically, I mean, this is a single particle band structure.
Yeah.
But the mechanism of populating this state is plasmonic origin.
Yeah. Okay. So it doesn't matter that the.
No.
Yeah, that makes sense.
Mhm.
Okay. Did anybody else have any questions that they wanted to ask?
Yeah. So first of all, I'm Rajan. I'm from CMU, and I do X-ray scattering.
Oh, okay.
And I also use femtosecond pulses.
Okay.
So I was curious why you need to use fast pulses for this experiment.
Because we need to excite nonlinear process, so we need a very high peak power. If it's a continuous laser or long power, then the peak power is pretty low, and we cannot expect this. The field strength is not enough to excite the nonlinear process.
I see. Okay. So then you have the two photon combination happening at the interaction with the surface.
We are using single color, so just one pulse.
Okay.
But it can absorb many photons from a pulse, right?
Mm-hmm.
So.
Okay.
Quick question too. I'm also from CMU, and I mostly do like RPEs on 2D materials.
Oh.
So these plots here on the bottom,
Mm-hmm.
we're looking at the photo emission energy and then some sort of intensity. And so is this kind of like you're averaging over momentum here and getting the energy, or
this is the line profile at gamma point.
I can't point.